In this video, we're going to look at conservative vector fields. We're going to describe simple and closed curves. We're going to define connected and simply connected regions. We're going to explain how to find the potential function for a conservative vector field. And I think we talked a little bit about this in class the other day when we were looking at 6.2, I think. We're going to use the fundamental theorem for line integrals to evaluate the line integral in a vector field. And we're going to explain how to test a vector field to determine whether or not it is conservative. So first, let's define what a closed curve is. A closed curve C, if there is a parameterization R of t such that t runs between A and B inclusive of C such the parameterization transverses the curve exactly once, when I go from R of A is equal to R of B, the curve C is a simple curve if it doesn't cross itself. That is, C is simple if there exists a parameterization, so that R of t from A to B for t, that R is 1 to 1 over A to B, not inclusive, and it is possible for R of A to equal R of B, meaning that it is simple and closed. So here's a couple of visual examples. This is a simple curve, but it is not closed. This is simple and closed. This is closed but not simple. See how it crosses over each other? And this is neither simple nor closed. It doesn't close itself. And of course it crosses. To determine if the curve is closed, that's the easy part. All you have to do is input the left and the right value of the interval. If the outputs are the same, then it's closed. That's the easy part. We'll relate an integral over a region to determine the boundary of the region, where the region's boundary is a simple closed curve of a union of simple closed, or a union of simple closed curves. So the region D is a connected region if for any 2 points P1 and P2, there's a path from P1 to P2 with a trace contained entirely inside the region D. A region D is simply connected region if D is connected for any simple closed curve C that lies inside D, and the curve C can be shrunk continuously to a point while staying entirely inside the region D. In 2 dimensions, the region is simply connected if it is connected and has no holes. That's nice. So we're going to use these 2 definitions. They're going to be valid for regions in any number of dimensions, but we're only going to be concerned with regions of 2 or 3 dimensions, at least in this class. Here is a simply connected region. Here's regions that they're connected, but they're not simple because they have holes in them. So that's basically what that was showing it, the definition. Now, not all connected regions are simply connected. Simply connected regions have no holes. Connected regions that are not simply connected have holes, but you can still find a path in the region between the points, the 2 given points. A region that is not connected has some points that cannot be connected by a path. So if we look down here, that we have these 2 regions, D1 and D2. These are not connected. I can't get from one island to the next, if you will, without getting in a boat and or getting wet, if those represent islands. So we needed that information to get down to the fundamental theorem of line integrals. So when we're in Calculus 1, we have the fundamental theorem of calculus for 1 dimension. We have, if we're integrating from a to b of f of x dx, this can be evaluated as the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. And if we think of this as the gradient as the derivative, then the same theorem is going to hold for vector line integrals. So here's our first theorem that we're going to use a lot. Let C be a piecewise smooth curve where the parameterization of R of t, where t runs between a and b inclusive, f is a function of 2 or 3 variables of first-order partial derivatives that exist and are continuous. Then the integration over the curve C of the gradient of f dotted with f of dr is going to be f evaluated at the r, the parameterization r, evaluated at b, minus f, the function, evaluated the parameterization r, evaluated at a. Basically, the gist of this, which is really nice, is that we can now calculate many line integrals. As long as we have a potential function, we can calculate the line integral as evaluating the potential function at the endpoints and then just subtracting the two. So that's really kind of nice. So computing the line integral, if f is conservative, two-step process, find the potential function or the antiderivative, compute the values of f at the endpoint c, and calculate their difference. Bam. That's kind of nice. Note, a function of one variable that is continuous must have an antiderivative. Therefore, a vector field, even if it is continuous, does not need to have a potential function. So we're going to evaluate this line integral using the fundamental theorem of line integrals. Now remember, this notation means we're doing circulation, so just something to note. So we're going to evaluate basically the circulation of this vector yi plus xj dotted with a dr, where c is a path, any path, from 0 to 1, from 0, 0 to 2, 4. So we're going to first start out with what our vector field is, and our vector field is going to be the x component, which happens to be y in this case, and then the y component, which happens to be x in this case. And this is going to give us our p comma q. Now then, our partial derivative of p with respect to y is 1. Our partial derivative of q with respect to x is 1. Oh, that's lovely. Since p of y is equal to q of x, we know this field is conservative. So now we want to get the potential function. What we know, this has to hold true. We know this has to hold true for conservative fields. That f of xy has to be the integration of p with respect to x plus some function of y. Simultaneously, f of xy has to be equal to the integration of q with respect to y plus some function of x. So these both have to hold true for this to be a conservative field. If it is a conservative field, it has to hold true. So let's go ahead and do this. First one, we're going to have the integration of p, which happens to be y dx, plus some function of y. So this is going to be xy is plus some function of y. Then we're going to do this one, and we're going to know this is going to be the integration of x dy plus some function of x. So this is going to be xy is equal plus, I don't know why I want to keep doing equal, because I really just like equal, plus h of x. Now, we also know that these two must be equal. Since those two must be equal, the only way that would happen is if g of y has to equal h of x, which has to equal 0. So then my function f of xy must be equal to xy plus some constant c. Now we're going to apply the fundamental theorem, which says the integration over the curve c of the vector yx dotted with a dr has to be equal to the integration of the curve c multiplied by the gradient of my function xy plus c dotted with dr, which is going to be equal to x sub f y sub f plus c minus x sub I, y sub I plus c, which basically gives us x sub f, y sub f minus x sub I, y sub I, which we know our initial is what the i's stand for, the f's are our final. Our x final was 2, our y final was 4. I wanted to use 8. I want to go right to the answer, which was 4, minus our initial, which both were 0, so my answer is 8. And there's my answer. And just to note, when I'm doing f sub f and y sub f, these are my final points, and my final points were 2, 4. And my x sub I and my y sub I were the initial points, which was 0, 0. Let's take a look at my next example here. We're going to find again the circulation, because that's what it means when I have this funky looking thing here with c, of 2y dx plus 2x dy, where c is the line segment from 0 to 4. So again, I know my initial, so this is x I and y I, and I know my final, so this is x final and y final. So that's kind of nice. So once again, we start with our field. So our field is going to be 2y comma 2x. This is going to be equal to PQ. We're going to make sure that this is a conservative field, so we need to check the partial with respect to y is just going to be 2. And we're going to find that this is actually going to be the partial with respect to x, so we know we are conservative. So now all I have to do is find my potential function. My f of xy is going to be the integration of p with respect to x plus some function gy. Simultaneously, my f of xy has to be equal to the integration of q dy plus h of y. So this is going to be equal to the integration of 2y dx plus g of y. This is going to give me 2xy plus g of y. I'm going to come over here and I'm going to do this integration. My q was 2x with respect to y plus h of y. This is going to give me 2xy and then plus h of x. This should be h of x. Change this to the h of x. And as before, you can see that the only way this is going to work out for these to be equal is if g and h, the only way this works out is g of y equals h of x, which is equal to 0. So then my function, f of xy, must be equal to 2xy plus some constant. I'm going to use that as before, applying the fundamental theorem, the integration over c from 2y to x. I don't know why I put a d there. So 2x, why do I keep wanting to do a parenthesis there? I don't know. Dotted with the dr is going to be equal to over this curve integration over the curve c of the gradient of 2xy plus c dotted with the dr, which is going to give me 2x of my final, y of my final, minus 2x of my initial, y of my initial, because as before, my c's cancel themselves out. And so I'm going to get my initial. So my finals were 4 multiplied by 4, and then don't forget the 2, and then the 2 multiplied by the 0, 0. My final answer is 32. So that's really kind of nice. Here's some important shakeouts of the fundamental theorem of line integrals. If f is a conservative field and c is closed under the curve, then the circulation of f along c is 0. That is, the circulation C of f dot dr is equal to 0, and we think of the vector field as an integral of the circulation of f dr as a gravitational field, then the equation is equal to 0 follows. The line integral of a conservative vector fields are independent of path, meaning they depend only on the endpoints of the given curve and not how you get there. That now gives us this. Let F be a vector field with a domain D. The vector field F is independent of the path, or the path, let me zoom out, or path independent, as we say, if the integration along the curve C sub 1 of f dr is equal to the integration along the curve C2 of f dot dr for any path C1 and C2 chosen within D with the same initial and terminal points. So if I take a look visually of what's happening, here's my vector field. I start here, I end there. I can go straight. I can kind of bird walk around this way, or I can go bird walking around this way. Either way, I'll get the same answer. Next thing we get is if F is a conservative vector field, then F is independent of the path. The set of conservative vector fields on an open and connected domain is precisely the set of vector fields independent of path, and this next theorem says if F is a continuous vector field that is independent of path and the domain D of F is open and connected, then F has to be conservative. So we must answer the following question. Given a conservative vector field, how do we find a function f so that the gradient of f is equal to the antiderivative of f? Here are some steps that we can do. We can integrate p with respect to x. This results in a function g of xy plus h of y, where h of y is unknown. We take the partial derivative of g of xy plus h of y with respect to y, which results into this function. We use the equation of this g with respect to y and set it equal to q of x, and we integrate h prime of x to find h of x. Lastly, any function like this where c is constant is a potential function for f. What? Let's go through an example. So here is my function, and I want to find the conservative vector field for the potential function. So the first thing we're going to do is find our gradient. So I'm going to find my gradient f, which is going to give me my vector field. This is going to be equal to the partial of my function with respect to x of f of xy, and then my partial with respect to y of f of xy. And this is going to be, in this case, is going to be, let me see, the partial with respect to x is going to be 10x plus 3y. And then my partial with respect to y is going to give me 3x plus 20y. And that's it. Now, if an object has a unit mass and is located at the origin, then the gravitational force in R2 that the object exerts on another object of unit mass at the point xy is given by this vector field. F of xy is equal to negative g, x, then I have x squared plus y squared raised to the 3/2, comma y, x squared plus y squared raised to the 3/2. If we are in 3 space, the negative g would still be outside, but I have x, y, and z in the numerators. The same kind of thing in the denominators, where I have x squared plus y squared plus z squared now raised to the 3/2 in each one of the denominators. And g is the gravitational constant. Now we're going to determine whether or not the vector field is conservative. So we have this theorem that says the cross partial test for conservative fields is thus. If you have p, q, and r in the positions x, y, and z, This is a vector field on an open, simply connected region D. Then, if P of y is equal to Q of x, and P of z is equal to R of x, and Q of z is equal to R of y, throughout all of D, then F is conservative. Now, if we combine this theorem with a cross-partial property, say that really fast, we can determine whether a given field is conservative. So, this theorem says, let F be this vector field where P, Q, R are the X, Y, Z positions, be a vector field on an open, simply connected region D. Then, let me just move this over. Then P, the partial with respect to Y, is equal to the partial of Q with respect to X, and the partial of P with respect to Z is equal to the partial of R with respect to X. And lastly, the partial of Q with respect to Z is equal to the partial of R with respect to Y throughout D, if and only if F, my vector field, is conservative. Now in R2, this theorem also applies. We just have to check the two. P of y, P with respect to y is equal to Q with respect to x. Nice, in 2 dimensions. This theorem 6.1 that we just talked about can only be applied if the domain of the vector field is simply connected. First thing we want to do is ask, if we are asked to calculate the integral of the form of the integration over the curve C of f dotted with dr, the first thing we should ask, is my vector field conservative? If the answer is yes, then we should find a potential function and use the fundamental theorem of line integrals to calculate it. Boom, done. If the answer is no, then the fundamental theorem of line integrals aren't going to help us, and we have to use other methods, which we will, of course, explore. And I know you're excited about it. So the first thing we're going to do is determine whether the vector field is conservative, and if so, find a potential function. So I know that this is going to be equal to, I'm going to write this as just 2xy cubed, 3y squared x squared. And I'm only in 2 dimensions, so all I have to do is check to see if P of y is equal to Q of x. So I'm going to do, and this is P and this is Q, I'm going to do my partial of P with respect to y. So that's the partial of this with respect to y of 2xy to the third, which is 6xy squared. My partial of Q with respect to x, my partial of this with respect to x, which is 3y squared x squared, which gives me 6xy squared. These are equal. So we know that this field is conservative. So now what I'm going to do is find my potential function. So we know P or f of xy has to be the integration of P with respect to x plus some g of y. Simultaneously, the integration of Q with respect to y plus h of x must also equal f of xy. So then this is going to be equal to the integration of 2xy cubed dx plus g of y, or g of y. This is going to give me, when I get done integrating, x squared y cubed plus g of y. I'm going to do this integration, so I'm going to integrate my q, which happens to 3y squared x squared dy plus h of x, which is also going to give me the x squared y cubed plus h of x. And of course, since these have to be equal, the only way these two are equal is if h of x and g of y is equal to 0. So then my f of xy is going to be just equal to x squared y cubed plus c, and that's it. So unlike my previous one where I did that substitution to actually find a value, I'm just asked to find the potential function. Looking at this next example, once again, I'm just going to rewrite it so it's easier for me. So negative y plus e to the x sine y plus, or then comma, x plus 2e to the x cosine y. So again, I'm going to check to see if my p with respect to y is equal to the q with respect to x. So I'm going to do my partial with respect to y. This is p, this is q. This is how I do my housekeeping. So I'm going to have 1 plus e to the x cosine of y. My q of x is going to be equal to, well, I'm just going to rewrite q to make my life easier. I'm going to rewrite q as xe to the x plus 2e to the x cosine y. So that way when I take my derivative, I'm going to get e to the x by the product rule plus xe to the x minus 2e to the x, the sine of y. Now, you can see that these don't match. These are not matched, so it's not conservative. So I can't find a potential function like I have been doing before. Let's take a look at my next example here. Again, I'm going to just rewrite this as 6x plus 5y, 5x plus 4y. I'm going to take p with respect to y. This is my p. This gives me 5. I'm going to do my q with respect to x. This gives me 5. These are equal, so this is a conservative field. So that means I can find my potential function. So f of xy must be equal to the integration of p, which is 6x plus 5y, with respect to x, plus g of y. Simultaneously, f of xy is equal to the integration of 5x plus 4y dy plus h of x. All right, doing this first integration with respect to x, we're going to get 3x squared plus 5xy plus g of y. Doing this integration, I'm going to get 5xy plus 4, which is 2, y squared plus h of x. Now this is the first time, by the way, that I haven't had them to be the same. So if I take a look at this, the thing that matches is the 5xy. So we know that our function has to have 5xy. F of x has to equal 5xy. Now, if I were to take this derivative and do this with respect, if I were to do this function and do this with respect, take this derivative with respect to x, then the g of y would go to 0. If I were to take this function and do it with respect to y, then the h of x would be 0. So that means a good choice for the g of y would be 2y, so plus 2y. And a good choice for the h of x would be plus 3x squared, and then all I have to do is tack on my c. And that's it. Let's take a look at my next example here, where I'm asked to find, again, I've got a whole bunch more derivatives in this. This is awesome. So this is going to be 2xy e to the x squared y. And then I have x squared e to the x squared y. So of course, the first thing I'm going to do is take my partial with respect to y. So p of y is going to be, well, that actually isn't too bad. It's the product rule, so it's not too bad. I'm going to do the derivative of the y part, which gives me 2x e raised to the x squared y plus 2xy e raised to the x squared y multiplied by x squared. So this is going to give me 2x e to the x squared y plus 2x raised to the third power e to the x squared y. Now I'm going to do my q of x. So my q of x is going to give me 2x e to the x squared and then y. Let me go and change this. This is a power, not a multiplier. So this is a y up here as a power. And I almost forgot this 6 to bring that 6 in. So I need to make sure I bring that 6 in. Okay, so, let me see. Let me erase this. So then this is going to be, this derivative with respect to x is going to be 6 multiplied by 2x e raised to the x squared y plus 6x squared e raised to the x squared y multiplied by 2x. This is going to give me 12x e to the x squared y plus, looks like another 12x cubed e to the x squared y. And you can see these don't match. These are not equal. So not conservative. All right, now we want to compute the integration across C of cosine x, cosine y dx minus sine x, sine y dy, where the function c of t is going to be t comma t squared, and t is going to run from 0 to 1. So the first thing we're going to do is write this as a line integral. So we're going to rewrite this as the integration across the curve C of cosine x, cosine y, comma, negative sine x, sine y, like that, and then dr. First thing we're going to want to do is prove that find out whether or not we have a conservative field so we can use the fundamental theorem of line integrals. If we can do that, life is pretty easy. So again, this is my P, this is my Q. So I'm going to do my P with respect to y, which is going to give me the cosine of x minus the negative sign of y, so a negative cosine x sine y. I'm going to do my partial of q with respect to x, which is going to be negative cosine x sine y. Well, that's lovely. We have a conservative field. So our next step, after we've confirmed that this is a conservative field, we're going to find the potential function, or the potential function. So we know that f of xy is going to be the integration of p with respect to dx plus some g of y. Simultaneously, the function of xy is equal to the integration of q of dy plus some function of x. So this is going to be the integration of the cosine of x, the cosine of y, dx plus g of y. This integrates pretty nicely. It's just going to give me the sine of x, the cosine of y, plus g of y. Integrate this. This is the integration of negative sine of x, the sine of y dy, plus h of x. This is going to give me, when I integrate negative sine of y is going to be cosine, so it'll be the sine of x, the cosine of y, plus h of x. So this is kind of like the ones that we had before that only happens when those two are 0. That means my f of xy must be the sine of x cosine of y plus some constant. Now we know by the theorem, when we integrate across the curve C of the cosine of x, the cosine of y dx, minus the sine of x, the sine of y dy, will be equal to my function evaluated at the final x, the final y, minus my function evaluated at the initial x and the initial y. And you're thinking, how am I going to find that? Well, at t equals 0, because we're going to come back up here and I have when t is equal to 0, I have the ordered pair 0, 0. When t is equal to 1, I have the ordered pair 1, 1. So my initials are 0, 0. I'm going to put into my function, and I'm going to put in, excuse me, 1, 1 as my finals into my function. My potential function, that is. So then this is going to be equal to the sine of my final, which is 1, cosine of my final, which is 1, plus my constant, minus the sine of 0, that's my initial, the cosine of 0, and then plus c. And you can see that the sine of 0 goes to 0. My constants will cancel. And so I end up with the sine of 1, the cosine of 1. And I can leave it like that if I'm so inclined. Or, because I love trig so much, this looks like a half angle type of thing. So I could write this, if I'm inclined, as 1/2 the sine of just 2. If I really wanted to do the double angle. And there's my answer. I'm actually okay with this answer, but if you want to say, impress me with your trig, you can do that too. And that's it for this video.